All right, this is the lecture on work and power. It says enjoy your sweat because hard work doesn't guarantee success, but without it, you don't have a chance. And that's Alex Rodriguez. So the goals for this lecture is to understand the factors that are necessary for work to occur. You should also be able to calculate power and work, and you should be able to relate work back to kinematic motion. That's the goal for this, is we relate it back to what we did at the very beginning of the year. So work is the action energy that supplies a force. So we talked about energy and defined it as the ability to do work. Well, work, it turns out, is a force times a displacement. So the key thing, though, is that the force and the motion must be in the same direction. Okay, if the force is going up and the motion is to the right, that's not work. They have to be in the same direction. So because of that, work can be positive if it's moving up and to the right, or it can be negative if it's moving down and left. Okay, and this question says, when lifting a crate, when do we do more work? When lifting this crate to the first line or to the second line? It's actually a pretty easy question. We don't actually need to do a whole lot of calculations with that. We know that work involves force times distance. Now, assuming that you're picking the box up with the same force, in other words, you're not just barely lifting it in one case and then throwing the box up in another, you can say that the forces are going to be equal. So really that means the only thing that determines how much work is done is the distance. And since this distance is twice as far as the other distance, you can say that lifting it to the second line requires more work. Okay, this question says, calculate the amount of work done on a box if a man applies a force of 812 newtons over the course of 28 centimeters. Now, the first thing that you should realize is we don't really deal with things in centimeters, so we're going to have to do something about that. But for now, let's say that we are looking for the work that is done. We know that the formula we have for work is equal to force times distance. We can say, all right, we have some sort of box that we are applying a force of 812 newtons to, and we're going to move that box a total of 28 centimeters. Went ahead and put a little star right there just to let me know, hey, centimeters is not something I'm going to deal with. So now we start to give these variables certain values. So we know that since force is measured in newtons, we know that this is going to be 812, and distance is centimeters. We have this. However, we need to convert to standard units, and we say there's 100 centimeters in 1 meter. Or our distance term is actually not 28, but is instead 0.28 meters. Once we have this, we can plug it into our formula. We can say W is equal to FD, or 812 times 0.28, and that would allow us to calculate our work, which is 812 times 0.28, or 227.4 joules. Now the last thing we want to do is we do want to make sure that our units match up. Remember, for work we have the unit of a joule. Okay, a joule is a kilogram meter squared per second squared. That's the definition of a joule. On the other side we have a newton. Remember, a newton is a kilogram meter per second squared. And then we have meters. When you multiply kilogram meter per second squared times meters, this term goes away, you have a squared, those two things are equal. This question says, calculate the distance that an object moves if a force of 164 newtons results in a total energy applied to the box of 19,500 joules. So remember, it doesn't specifically say work in any of these questions, but it does give you the total energy. Remember, work is an example of energy, so we can say, all right, I've got some sort of box that I'm pushing with 164 newtons of force. I know somehow I'm going to get 19,500 joules out of that. So now I know I'm trying to figure out what the distance that the box has to move is. So how far did it go for that change in energy to occur? So since we're looking at work, we can say work equals force times distance, or we can start to assign our variables. We know that anything that's measured in newtons is an example of a force, so we say F is 164. And we can also say that since this is measured in joules, it has to be an energy, and an energy would be work, 19,500 joules, and that allows us to solve for distance. We can say W equals FD, or rearrange, divide both sides by F, and you get D is equal to W over F. Or in our case, we would have distance is equal to 19,500 divided by 164. When you do that division out, you get 118.9 meters. Now we want to make sure what we did is algebraically correct. So we take this unit right here, which is joules, 19,500 joules. Now remember, a joule is a kilogram meter squared per second squared. So we have kilogram meter per squared per second squared, and we divide it by a newton, which is a kilogram meter per second squared. Okay, we want those things to equal our unit of meter. So we look at it, we say kilograms on top, kilograms. Second squared, second squared. 1 meters, meters squared. So the squared term goes away, and our unit matches up.
Now, we don't always have the force and the displacement moving in the exact same direction. It could be that you have a force that's being applied up and to the right, and you have a box that's sliding directly across the floor. And so in that case, there is some aspect of those two things that are moving in the same direction, but they are not entirely. So you can't just multiply a force that's moving up and to the right at, say, a 45-degree angle, and a displacement that's moving straight across the floor. You can't just multiply those together. So instead, you have to account for the angle. And so whenever there's an angle in these work calculations, work is equal to F cosine theta d. Okay, what this is this cosine theta actually takes out the one component that is the same as the displacement of the object. So really what you're doing is you're saying, okay, I have a force that goes up and to the right, but what I'm going to do is I'm going to take the just rightward component and multiply it by the displacement. This only works because, once again, work is a vector, so you can take out those individual components.
Alright, this example says determine the work done pushing a box with a force of 100 newtons at an angle of 45 degrees, a total horizontal distance of 10 meters. So this is one we really do want to draw out. So we have a box that starts right here, and we want to move it a total of 10 meters. Okay, I'm applying the force at a 45-degree angle. There's a couple of reasons why we would do that. Applying it at an angle would actually reduce friction, so that's one of the reasons why we could do that. But really, we're applying it at an angle, so we can no longer say work equals force times distance. And the reason why we can't do that is this force and this distance are no longer in the same direction. So we can't just simply say W equals FD. Instead, we have to expand our formula and say W equals F cosine theta D. And what this does is this actually takes the x component of our triangle, we'll call it fx for now. Okay, that's what we're doing, is F cosine theta is really fx. It's the part of this force that is in the same direction as the distance. Okay, unless you have some sort of value, you can't have work occur. So we are trying to solve for work. Okay, the values that we have, we are given a force of 100 newtons. We are given a distance of 10 meters. And I can't tell you how many times people on a test would just multiply those two and get 1,000. But really, we have to account for the angle. The angle is 45 degrees. Like when we do all our calculations, we need to make sure that our calculator is in degree mode. How you do that is you hit the mode button. And if you look, degree is the one that is highlighted. That's the one that I want to be in. So now we say 100 times cosine of 45 times 10, and we get our value of 707 joules. I guess I should have written this out as 100 cosine 45 times 10. But you get 707 joules out of that. Okay, this is a question that they like to use on old tax tests and things like this. This is how much work is done in lifting a car. Now, so we are looking for the work value. We do know that we are taking a car and we are lifting it up. Okay, so the force that we are actually opposing is the gravitational force. Now we're going to assume that we're lifting this thing at constant velocity, okay, because it doesn't really make sense to accelerate a car up. So if this thing is moving at constant velocity, I know the force upward has to equal the force downward for a constant velocity to occur. So the force upward, I can actually say is equal to the weight. So now if we look at our formula, W equals Fd, I also have the formula F equals mg because we're talking about weight. So I can actually substitute that in and I can come up with a new working equation that I'm going to say is W equals mgd. Now, in this particular example, it says that we have a mass of 1,700 kilograms. So let's go ahead and say we have an M of 1,700 kilograms. We have gravity. We're going to assume that the car is on Earth because that's where all the cars that I know are. And we have a distance that we raise it as being 2 meters. So now once we have these three variables, so these three variables that don't seem to necessarily fit in this equation do when you combine these two together. Now a lot of times people will forget this 9.8 factor, and what they'll do is they'll just take the mass and multiply it by the distance. That doesn't work. Remember, if you were to look at the units, they wouldn't match at that point. And we'll show you what we're talking about in just a second. So now we would multiply this out, and we would say 1,700 times 9.8 times 2, and that's going to be equal to our work value. So we enter it into our calculator, 1,700 times 9.8 times 2, and we get a value of 33,320 joules. Now just to show you what we were talking about with the units, okay, if I would have just taken mass and multiplied it by distance, okay, what I would have on this side is I'd have kilogram meters. But on the other side, the unit for the joule, remember, is the kilogram meters squared per second squared. Those two things are not equal. So it lets you know that there's something missing. And remember, the unit of gravitation, or the acceleration due to gravity, is meters per second squared. Okay, when you add this term in, you clearly see that the units will match. You'll have kilograms, meters squared, and seconds squared. So please do not forget this G term. It's the most common mistake on this type of problem. Okay, this question says the lawnmower is being pushed horizontally with a force being applied at 90 degrees relative to the direction the lawnmower moves. It says the lawnmower moves a total of 15 meters. What is the energy that is a result of this action? And a lot of people look at this and say, okay, I got an angle, I got a distance, where's the force? And then they'll try and look for weight, or they'll try and look for mass. I purposely left those out because I wanted to show you something. Remember, the force and the movement have to be in the same direction. In this case, it tells me they're 90 degrees to each other. Okay, so just to show you, W equals F cosine theta times D. Now I did give you a distance, but I didn't give you a force. But I wanted to show you this right here. So if you were to take this and put into a calculator, cosine of 90, you would get a value of 0. So what that's showing you is that whenever you exert a force straight up and down, there is no x component. So there's no part of a straight up and down force that acts left or right. So this term is zero. 0 times anything is 0. 0 times anything is 0. So the work that's done is 0. And you say, well, wait a second, there's still movement and so forth. Remember, work requires a force and a movement in the same direction. Okay, since there is no component of the force and displacement that are in the same direction, there is no work done, regardless of the amount of movement that's occurring.
All right, so power is really important. Power is the rate at which work is done, but more specifically, it can be used for any energy. So power is measured in the unit of the watt. Okay, the watt is the joule per second. So any sort of energy, it could be kinetic energy, which we'll learn about, electrical energy, no matter what it is, any sort of energy divided by time gives you the rate at which energy is used. And that's actually very, very important when we're talking about things in terms of efficiency of engines and how quickly something can move and so forth. So this is a really key term.
All right, this question says calculate the power of a weightlifter who lifts a barbell from the floor to 2 meters above in 3 seconds. So we are looking for power, just capital P. And the formula that we have is power is equal to work divided by time. Okay? So when we take a look at this equation, we say we have some sort of weight that we lift 2 meters above the surface of the earth, and the time that it takes is 3 seconds. This thing right here is 50 kilograms. So if you notice right away, the only thing that I'm really given is the time. I'm not given anything else. So this is one of those questions where you're going to have to expand the formula out. So we'll start with the idea of work. I don't really know what the work is, so what I'm going to do is I'm going to substitute in what work is equal to. Force times distance. So that means that power is equal to force times distance over time. But even that's not really helpful. So what I'm going to do is I'm going to say, okay, well, F is also equal to MA. And when I do that, I get power is equal to MAD over T. Okay, so now generally at this point, people say, well, how am I supposed to get from here to here, and how am I supposed to know how to do that? It's just by expanding these out like we did, substituting them in for one another. If you're not comfortable with that, you can always just say, instead of substituting it in, okay, well, how do I get work? Okay, well, how do I get force? And then doing those individually instead of substituting them in. Now, this particular one is pretty easy to memorize because we say it this way. Physics has the power to make you mad over time. So it's just an easy mnemonic way for you to try and remember that. So now if we look at our given information, we're given a mass of 50. We're given an acceleration of, we're not given an acceleration, but we are lifting it off the ground, so we should know that our acceleration should be equal to 9.8. And then we also have the distance that we go is 2 meters, and the time that it takes for that to occur is 3 seconds. So we do 50 times 9.8 times 2, all of that over 3. So we can now multiply that out. 50 times 9.8 times 2 divided by 3, you get 326.7 watts. The unit of power is the watt. Okay, in this example, it says an engine produces 1.4 kilowatts of power, so you should know, hey, I got to do something with that. In lifting a 100 kilogram object, what is the velocity of the object as it is raised? So this is an interesting question. So what we want to do is we want to say, okay, I am looking for velocity. Okay, well, if I'm looking for velocity, I know that I want to take an object and I want to lift it up in the air, and I know I have a power that's occurring. So I do want to use my power formula, P equals W over T. Now, one thing that you'll notice right away is I don't have, well, I don't have a time, I don't have work, I do have power. You say, well, why is this formula relevant? I'm trying to find velocity. Well, let's look at what we know about velocity. Velocity is equal to distance over time. I don't have that either. Okay, I don't have distance, I don't have time, I don't have any of those things. So the question is how can I get these things to relate? And it's this way. Remember, power is equal to work over time, but work is force times displacement over time. Now, if you look, d over t. So what we're really saying is power is equal to force times velocity. Now, the object is moving at a constant rate, okay? Because in order for it to have a steady velocity term, it has to be moving at a constant velocity. That means that the weight downwards has to equal the force upwards, okay? That's our free body diagram stuff. So if we know this is occurring, we can say, okay, well, this F really represents the weight, or in our case, mass times gravity times velocity is equal to power. And if you look, lo and behold, we have power, we have mass, okay? So we can go ahead and we can solve for velocity. So our power that is given to us is 1.4 kilowatts. Now remember, anytime you see the kilo prefix, you know that you can convert whatever value it is. You can say 1 kilo, in our case watt, is equal to 1,000 watts. So when you do this, you get 1,400 watts. Okay, you have a mass value that is given as 100 kilograms. And finally, G is 9.8. So we can say, all right, mass times gravity times velocity is equal to our power. Take this, divide both sides by 980. And the reasons why I would divide both sides by 980 is because 100 times 9.8 is 980, and I want to get rid of it. So when I do that, I would say 1,400 divided by 980, and that gives me a velocity of 1.43 meters per second.
So now you should understand the factors that are necessary for work to occur. You have to have a force and you have to have a displacement, and they have to be in the same direction. And if they're not, you have to be able to take the component of the force or the displacement and then apply it so that they are in the same direction. You should be able to take the formula where work is equal to force times the distance, or force times cosine theta of the displacement, and you should be able to figure out what the power is, what the work is. Once you have the work or the energy, you should be able to turn around and you should be able to figure out what the power is. Finally, you should be able to relate this back to kinematic motion, because we now have an energy, and if we have a displacement, which is one of our key kinematics terms, and we have a force, and remember, force is really just mass and acceleration. So contained within the work value or the energy value, you have acceleration and you have displacement, which are two of the key things that we're talking about when we're talking about kinematic motion.